Awesome. So let's just get started with whatever first question you want to look at.
Okay. And we attempted doing part A, the displacement of the car from the point of origin, and like using right triangle trig, and it was
We did like the Pythagorean
wrong.
theorem, and it was wrong.
And we did like SOHCAHTOA,
SOHCAHTOA.
and it was wrong. And it was wrong.
If
So we thought it
SOHCAHTOA's
was
not
like-
working, then you know you're in trouble.
Yeah. Or the Pythagorean theorem, right? Like it's,
Yeah.
yeah.
So let's take a look. A car is driven 230 kilometers west and then 98 kilometers southwest, so 45-degree angle. So let me just go ahead and get that written, and then I'll give you your iPad back. So here's our XY coordinate system, right? This is the way we look through the world, or look at the world.
Right.
And we've got a car that's going straight west. So right along that x-axis in the left direction. And then they go southwest at a 45-degree angle. So that would be like that. Oops. And this is 230, and this is 98. Let's make that shorter so it's a little bit more to scale. Cool. And so they're asking for the displacement for part A,
Yeah, and it says in parentheses the magnitude.
the magnitude.
Yeah.
Yep. So the displacement, just visually, we can kind of guesstimate it. We can say, well, we know our car started here and it ended here. So if we just wanted to eyeball the displacement, we would just connect those two dots. So we'd say, here's our displacement. But the question is asking for more than that. They don't want just a general picture. They want to know a number that we can attach to this displacement. So let's call that D. So the way that we can do that is by breaking this vector here, the 230 west, that's pretty much already broken into components because it's only in the x-axis. There's no diagonal slant to this vector. It's just totally flat right along the x-axis. So if we wanted to break this into x and y components, we would say the y component equals 0 and the x component equals 230. Or we might call it negative 230 if we want to remind ourselves that it's going left, because usually we think of left as negative. This guy, however, it is on an angle, so it would be helpful to break it into its components. So what we can do is if we look just at this 98 kilometer vector, we can say, well, right now it's on a slant, but I know that it's really just made of an x component that goes that far left and a y component that goes that far down. And so now we've got a right triangle. So we know that that's a 90-degree angle right there between our x and our y components. We know that our hypotenuse is 98 kilometers. We know that this angle right here is 45 degrees. Let's get it a little bigger. So we want to figure out how long that side is and how long that side is. So the way that we can do that is with some SOHCAHTOA magic. So we know that this angle is 45 degrees. We know the hypotenuse is 98 degrees. Relative to this angle right here, what is the label that we use to designate this side of the triangle? What do we call that side relative to this angle?
Adjacent.
Adjacent, good. So here's our adjacent side, and then this guy is called,
Opposite.
here's our opposite side. So we've got a couple different tools in our arsenal. We know that sine of theta equals opposite over hypotenuse. We know that cosine of theta equals adjacent over hypotenuse. And we know that tangent of theta equals opposite over adjacent. So we know the theta, and we know the hypotenuse.
So we're just trying to find the two sides, right?
Yep.
For this, okay.
So let's say we want to find the opposite side first. We would just plug into this because we know the theta, we know the hypotenuse, we're looking for the opposite. So do you see why that is a good choice? Because we can plug in here and here and then solve for our opposite side. So we can say sine of 45 degrees equals opposite over 98. So to get rid of that denominator there, we can multiply it over. So we'd say 98 times sine
That's what we got.
of
Yeah,
45.
I think we did this.
And what did you
And
get?
we got
Yeah.
69.3, but that's like not the answer.
Oh.
Not yet.
I think that we were
69.
getting to this point, but we didn't know where to go after this. We thought that was just the end.
So that's what you got, 69.3?
Mm-hmm.
So now we can say this is 69.3. So that's the y component. And since it's a 45-degree angle, we know that this is going to be 69.3 as well. That's just, does that make sense, or do you want to walk through that?
No, I get that.
Okay. Because yeah, with 45-degree angles, both our opposite and our adjacent side are always going to be the same number. So once we find one, we know what the other one is.
Yeah.
So that's our x component right there. So now we've got a bigger right triangle to deal with. Now instead of just looking at this guy right here, we're going to look at this whole thing. You see that?
Mm-hmm.
So now we know that, let's get rid of that. We know that this side of our triangle along this x-axis is going to be 230 plus 69.3.
Mm-hmm.
So that's going to be 299.3. And then this side is just going to be this 69.3. And now we want to look for our hypotenuse. So now we can use Pythagorean's theorem. Here's our A side, here's our B side, and we're looking for C. So now we can plug into A squared plus B squared equals C squared.
So I got 307.2.
307.2.
Mm-hmm.
So you said 299.3 squared
Yep.
plus 69.3 squared,
Mm-hmm.
and then you took the square root of that,
Mm-hmm.
and you got,
307.2.
there's our answer, kilometers.
Yeah, 1/6.
So yeah, we had to use a combination of Pythagorean's theorem and our SOHCAHTOA stuff.
We were just doing one big
Yeah,
triangle.
we just did one big triangle.
So you tried to just do this weird shaped triangle where it was
Yeah.
this and then this.
Oh.
Yeah, well,
yeah.
no, we
So
didn't
that
know it was
doesn't-
weird shaped until
Yeah, so-
we were thinking about, okay, west and south.
Yeah, Pythagorean's
'Cause we
theorem
just made a right triangle.
And sine, cosine, tangent are trig
Okay.
functions. They're really helpful, but they only work with right angle triangles.
Okay.
Since this triangle isn't a right angle triangle.
That's why we were
that
confused,
makes
because then
sense.
we thought about
Yeah.
the fractions and we were like, that's not a right triangle, so
Good.
then we
Yeah,
had to
so
go
then
down.
we didn't know what to do after that, but.
Perfect.
But we
So
did get
this
to
is
the
what you know.
69.3.
Yeah, so you were really,
So
really
if you want
close.
to ask for the direction of the displacement, what would that be? Sorry.
Because
Okay.
the second one is asking what is the displacement of the car from the point of origin and then direction.
So vectors, like we've talked about a lot of times, are magnitude and direction. So we just figured out the magnitude, but now we want to be able to explain numerically which way it's pointing. So the best way to do that is if we figure out what this angle is right here, so right now we'll just call it theta. Once we figure out what that is, then we can say, let's say it ends up being 20 degrees. We can say this vector is 20 degrees south or 20 degrees below of the negative x-axis.
So it's just asking for the angle.
And then it wants us to give that angle some reference. So we couldn't just say, oh, it's 20 degrees, because that wouldn't make any sense.
Right.
But we have to say 20 degrees from something. So we usually say, we use our axes as our reference points. So since it's closest to this axis, this is the negative x-axis, we would say 20 degrees below the negative x-axis,
Okay.
or whatever this theta ends up being. So now let's find out what this theta is. So to do that, we'll go back to our trig functions, and we can say, well, we know We actually know all three sides of our triangle, so we can use any one of these trig functions that we want. Let's just go ahead and use our adjacent and our opposite. So what trig function uses adjacent and opposite? Tangent. So we would say tangent of the angle that we're looking for equals opposite, which is the 69.3, divide adjacent, which is the 299.3. So then to get theta by itself, we're going to end up doing inverse tangent times whatever this ends up being. So 69.3 divided 299.3.
So 13.03.
13.03?
Yeah.
So theta equals 13.03 degrees. To give that number some context, we would say 13.3 or 13.03 degrees below the negative x-axis. Does that make sense?
Yeah.
So now we've found out the magnitude and the direction. Any questions about that?
No. That makes sense now. We just
Yeah.
had a hard time.
Yeah, you'll get
getting
lots of
past
practice
that
with
part.
So
it.
it's like, I don't think I could
I
do
know.
that on my own. Like, watching
Yeah.
you do it makes perfect sense, but like, if I got that problem again, I don't think I could.
Yeah, it's always good to look for the right triangles.
Yeah.
So here, originally we didn't have any right triangles, so the first thing that we did was we took this diagonal vector, we turned that into a right triangle. Once we figured out everything we can know about that right triangle, then we made our big right triangle. So it's just going from one right triangle to the next and trying to figure out what we can learn. And whenever you see a diagonal vector, so if a vector is not lying right on an axis, you always want to split it up into its components.
Okay.
Because working with slanted vectors is just tough. So we
Yeah.
always just split it into the x and y component.
Okay.